For example, on a smoothly changing curve, there's a constantly changing slope. How then, in today's language, is a slope calculated at any given point? To determine the slope at a particular point, here for example, simply take another point on the hill. It doesn't matter where. Now connect the 2 points with a straight line. That line is called a chord, and its slope depends on the location of the second point. If the first and second points are reasonably close, the chord is a reasonably good approximation of the bike's path. Now, move the second point closer to the first. Move it even closer. The slope is a number, and as the points get closer together, the number gets closer to a certain value. It's reasonable to call that number the slope of the hill at that point. The line with that slope through the point is called the tangent line. And the tangent line is just what the chord turns into as the points get closer together. And the slope of the tangent line at that point is the slope of the hill. Once the simple mechanics are mastered, finding the derivative for just about anything is no harder than flipping a switch.
The derivative of a function is the slope of its tangent at each point. The derivative of a function is itself a function. Then dy over dx equals cosine x. If y equals cosine x, then dy over dx equals minus sine x.
Taking derivatives takes a little practice, but it's well worth the effort. And considering any number of contemporary derivative machines, it's become a modern practice. A speedometer is a derivative machine. It measures the derivative of the distance traveled at each instant along the way. The rate of change of position is the instantaneous speed, expressed as miles per hour. Of course, when the vehicle isn't moving, no distance is being traveled. Here, the position is constant, and the derivative of a constant is 0. Mathematics is a language built on grammatical structure, a collection of rules that both builds and breaks down the composition of the task at hand. Whatever the masterwork, from building a house to composing a symphony, the most complicated task can be broken down in much the same way. Newton and Leibniz developed the tools of calculus that permit the most complex function to be differentiated by breaking it down into simple parts. One of the basic rules of differentiation is the sum rule. Suppose one painter can paint 90 square meters of wall per hour, and the other 100. Those are the rates at which areas of the wall are changing color. In other words, they're derivatives. Therefore, every hour, 190 square meters of wall are being painted altogether. That's how the sum rule works. The derivative of the sum is the sum of the derivatives. Another handy tool is the product rule, which is used to find the derivative of the product of two functions. For example, the area of any board is the product of its length times its width. If the length is shortened, change in area is the width times the change in length. If the width is reduced, the change in area is the length times the change in width. The total change in area is the sum of these. That's true of the carpenter's product, and it's just as true in the language of differential calculus.
The derivative of the product y times z is y times the derivative of z plus z times the derivative of y. Using this rule, it's possible to find the derivative of x squared. Or of x to the third power, or of any power of x. The derivative of x to the power n is n times x to the power n minus 1.
Often, one operation is dependent on another. For example, suppose a vehicle has a fuel efficiency of 17 miles per gallon. That, too, is a derivative. If y is the distance traveled and x the amount of fuel consumed, then 17 miles per gallon equals dy over dx. Say it uses 2 gallons every hour. 2 gallons per hour equals dx over dt. A vehicle's speed in miles per hour is equal to the miles per gallon it gets times the gallons per hour it uses. This is the chain rule. It's used when y depends on x, and x depends on t. The sum rule. The product rule. And the chain rule. These three rules represent the grammar of differential calculus. And the value of differential calculus can be seen in the variety of its applications. For example, when a rocket moves with displacement s at time t, the derivative of the displacement is the velocity. Positive for upward motion and negative for downward motion. The derivative of the velocity is the acceleration, which is the same as taking the derivative of a derivative. That is, the second derivative of s. The acceleration is caused by the firing of the rocket.